All right, so the last day we were introduced to what the rate law is, and it is essentially a mathematical equation that relates the rate of a chemical reaction to the initial concentrations of the reactants, all right? And it's got a particular form. We looked at what that form looks like. The rate is equal to some constant K times the concentration of reactant A to some exponent X, and the sum times the concentration of reactant B to some exponent Y. And if there was a third reactant, you'd have a C and a Z or a D and whatever, various exponents. And as I stated in the last lesson, that it is the purpose of the chemical kineticist, the guy who studies chemical kinetics, to determine what that rate law is, and that can be determined either by experiment, which is what we're going to look at today. How do we determine what those exponents are experimentally? And then ultimately, it's also the purpose to determine what that rate law is from theory, because depending on how the particles collide with each other, that's going to determine the way they react, and it's going to determine the rate. And again, we want that theory to be in support of the experiment, and hopefully then you get a true understanding on what's happening inside the chemical reaction. So for today's lesson, essentially, we just want to find out what X and Y is. Once we've done that, we can ultimately get K, and once we have the entire rate law expression, we can figure out what the R is, and we can use that equation to calculate various rates. Essentially, for today's lesson, it's pretty straightforward. I've got two examples, and then I've got like hundreds of practice problems. Okay, maybe not hundreds, but I've got a sheet with 6 of them, and then the new textbook has, I think, 6 or 7 of them, and you can practice, get this all figured out, all right? So to start with, unfortunately, you've got to copy this big, long example. And again, I've only got 2 examples, but once we have it figured out, I'll let you try them, work on them. And also, unfortunately, by the nature of the question, they always involve tables of data, which with this example and the next example are the only 2 times you have to actually write it out, because I have all the data on these sheets. The questions have all the data on it. Any test questions have data on it, etc., etc. Now again, just to relate this to what we've done in the past, so last week I introduced you to how we calculate rates. We can do an experiment. We can measure, say, the production of a gas like we did in our experiment. We can take that information on the production of a gas. We can make a graph, and we get a graph that has a particular shape depending on whether it's products being formed or reactants being consumed, concentration versus time, and we can determine various rates. And you're now all discussing and debating on, the lab, which is due tomorrow, which is great. How we can get an average rate or an instantaneous rate and all that good stuff. And in order to do a rate law determination, we do not want the products interfering with what's happening in this chemical reaction, because we want to get a sense of what's going on in the forward reaction, all right? And if the reaction is reversible, if we go anywhere beyond the initial rate, anywhere out into this, part of time, then the reverse reaction is starting to take place if it's reversible, all right? So we want to look at this chemical reaction from the standpoint where we're only looking at the reactants reacting. And therefore, the only good bit of data that we really want to take from, like, our experiment from last week is that initial rate, the slope of the tangent right at the very beginning of the chemical reaction, all right? That's really the only good data that will not have any products interfering with what we're trying to look at. So essentially, if we wanted to do a rate law determination ourselves, say as a, maybe even as a group, we would need to do our experiment, like with our production of hydrogen gas, multiple times. And each time, change the concentration of various things. Change the concentration of hydrochloric acid. Do it again. Take that initial slope. Excellent. Write that initial bit of data down. Do the experiment again with a different concentration of hydrochloric acid. Get the data. Take the initial slope. Write that information down. So we would have to do the experiment multiple trials, changing the concentration of different reactants and gathering all of that data up. Now, for our reaction, what did we have? I think we had zinc, or no, it was magnesium metal plus HCl. Magnesium is a solid, which means I can't really change the concentration of it. It is what it is. It's a hunk of solid. So the only thing I could change is the concentration of the HCl. So that wouldn't be that, big of a task. Maybe complete the experiment 4 or 5 times with different concentrations, gather up some data, and then, try to determine a rate law. When you're dealing with something that's more complicated, that has 2 or more reactants, you have to run the experiment, change the concentration of just one reactant, take the initial slope, change the concentration again, leaving the second reactant constant. Because really, we're doing a true experiment where we have to have an independent variable, a dependent variable, and a controlled variable. Because we want to figure out what the effect on that dependent variable is without messing it up by changing too many things. And that's really the place where we're going to start this analysis. If I want to determine the exponent on the ClO2, then I'm going to want to pick trials such that the concentration of the ClO2 is changed, right? So 1 and 2 isn't good, because we've kept those concentrations constant in those runs. So I need 1 and 3 so I can see the effect, well, not necessarily 1 and 3, but I need either 1 and 3 or 2 and 3. I want to see the effect of changing the ClO2, but I also must pick trials where I've kept the OH concentration constant, because I only want to see the effect on the ClO2. So if I'm looking for the effect on the ClO2, which trials am I picking here? Which trials are going to be the 2 that I'm going to want to compare in order to just see the effect of changing the concentration of ClO2? Yeah, Caitlin? 1 and 3, because that changes the ClO2 but keeps the OH constant, all right? Because I have to have a controlled variable. In this case, the OH is the controlled variable. When I want to take a look at the effect by changing the concentration of OH, I need to pick two trials such that the ClO2 is constant. Which trials am I going to use for that? Yep, 1 and 2. So 1 and 2 are constant there, and we're obviously changing it there. All right? So we must pick appropriate trials so that we only have that changing situation. Okay, let's talk about how we're going to analyze this. I'll go back to the slide if I need to get some data. And again, there are two ways in which we can solve this. The textbook likes, the old textbook likes to use a very logical way. Okay, what happens if we double the concentration? What does it do to the rate? And it's going on the assumption that, we're not good with mathematics. And I'm going to go on the assumption that you guys are pretty good with mathematics. Let's start by writing down just a general rate expression. Pen doesn't want to work. So, rate, and I'm going to put 2 first. Okay. Just like last day, we compared the rates when we were changing some information. So I had a rate during trial 2 and a rate during trial 1. That was the same on Friday. So rate during a second trial is equal to K, and I'm going to use some general reactants here because I want to come up with just a general equation for now, and then you can apply it to whatever equations you get. So again, I'm going to use A and B. The concentration of A, 2x. So this means the concentration of A in the second trial. And that's equal to the concentration of B, again, 2y. Okay? What I'm essentially doing again is I'm coming up with that relation equation that we did on Friday. But this time I want to put the 2 on top, just because I like to put the 2's on the top. When I mathematically did this myself, I was always more comfortable putting the 2's on the top. So rate for trial 1 that we're going to compare it to, again, equal to K, concentration of A in trial 1 to the exponent x, and the concentration of B in trial 1 to the exponent y. I'm going to do a little cheat move here. I should rewrite it with 1 equal sign, but in the end, I just want to divide off these two things. All right? And I'm going to be able to cancel out the k's, because I don't want to have to deal with the k's at the beginning. And that's going to give me an expression of rate 2 divided by rate 1 is equal to the concentration of A2x, the concentration of B2y, over the concentration of A1x, concentration of B1y. All right? Now, at this point, we have to start making some decisions in that if I want to study the effect of rate on the concentration of A, so if I want to study that relationship between the rate and A, what's that proportionality? As we've already discussed, what must be true about B if I'm studying the relationship on A? Yep. It has to be constant. So if I'm studying the relationship of A, the concentration of B must be constant. Another way of writing that is that B2 must be equal to B1. Okay? I could write that out, but that doesn't do you any good. I'm not needing to see the derivation of this. When I ask you to do a problem, I don't need to see this derivation. All you got to do is use it. But I find it useful to help understand by explaining the thing. So if B is constant, then I can also say that that is gone. And therefore, I now have an expression of rate 2 over rate 1. And again, I can take that exponent x out of the brackets here. I can put it outside of some brackets. Concentration of A2 over the concentration of A initial 1 to some exponent x. Now, I will tell you right now that with the types of problems that we give you, maybe on the page I've given you some trickier ones, you should be able to figure out the exponent x right there just by looking at the numbers you get. Because you're going to have R2 and R1, and you're going to have this one and this one, and you'll see that we've got something like 4 equals brackets 2 to the exponent x, and you've got to figure out what the x is, and it's not going to take you much to figure out that it would be 2, right? 2 squared is 4, and so the relationship is a squared relationship. So usually you can figure it out from here. But there is a mathematical trick that allows you to determine what the x is, even if you don't see the relationship. It's a very simple mathematical trick, and it's a trick that we used to use in science before you had all the computer programs and all this stuff to determine what the exponent was. Now, to be honest, I never personally used this method, but the method does work really well. This has to do with a mathematical relationship that you can use, that you've probably learned, that deals with logarithms. And I'm not going to write this. Actually, I will write it down, just up here in the corner. You don't have to write this down, but recall for the mathematics, if you have something like, goodness gracious, a to the exponent b, and you take the log of a to the exponent b, what does that become equal to? What can you do with that exponent b when you take the log of that particular thing? You would have learned this in math, I don't know, maybe last year. Did you work with logarithms? Yes, no? There you go. It's Monday morning. We got 2 people right beside each other, probably sat in the same class. No, I have no idea what we're talking about. Yeah, I remember that. That's exciting stuff. You're all sleeping right here. All those hockey players are just... Anyway, that's fun. This is what it's equal to. It turns out that you can take that exponent b and put it in front of the log, and you end up with b log a. All right? So this is the neat little trick that you can do. If you take the log of both sides of this equation, log R2 over R1, all right? Log concentration of A2 over the concentration of A1 x. What can happen there is that x can go out in front of that statement right there. Log R2 over R1 is equal to x log concentration of A2 over concentration of A1. I apologize, I put that 2 on the inside. I've been putting on the outside. And what that means in the end is log R2 divided by R1. And if I divide this whole term, bring it on underneath, over the log of A2 over A1, that is equal to x. All right? That's another way of doing curve straightening. If you, and we used to teach, well, actually, I've seen old physics high school books where we used to teach this log-log method. You'll notice here, we've got the log of rate 2 over rate 1, and that's over log of A2 over A1. You used to be able to get this paper that was called log paper, and it wasn't regular graph paper. It actually had changing sizes of squares, which means it was graphing the logarithms. And you could then you could graph the logarithms, right? The log of your rates on one side and the log of your concentrations on the other side. And whatever that slope was, log of the rates over the log of the concentrations, that was your exponent. It's a really neat trick. All you had to do was graph the logs of anything you didn't know the relationship for, and whatever the slope of the line was, that would tell you what your exponent was. That was before computer programs that would just spit the exponent out for you, right? Because it's doing the same thing. That's what the computer program is doing. In reality, to do this properly, we should be graphing vast numbers of data in order to get the true relationship between those concentrations. But because I'm just initially telling you this is an introduction to this, we're not going to have you graph vast amount of data. All we're going to have you do is compare two trials, figure out what the exponent is, and get the rate law. All right? So at this point, I'm going to clear this screen, and then we're going to start in on the problem that we're just working on at hand here. Again, I don't need to see this derivation. I just need you either to use this or even just use this, because you'll probably be able to get the answer right from that spot anyway. You probably won't have to use the log method unless you like to. I do. I dive right in. I write the numbers down. I run it through the calculator, and I just do that as a check, even though it's an obvious thing to do. Okay, so I'm going to clear the ink here. Nope, that's not how I'm going to do that. I'm going to do it like this. And now I'm going to take a look back at my data, and I'm going to look at the exponent on the ClO2 to begin with, which means what did we need for our trials? I needed the OH to be constant, so I needed trials 1 and 3, right? 1 and 3. So essentially, and now I'm going to need some of your help. So in order to determine, so 4, and this time I'm looking for the concentration of ClO2. I'm looking at trials 3 and 1. And I always write that down. I pick my trials, okay? Now I know that the rate law is going to have the two things in it, but now I'm only looking at ClO2. And I'm just going to go back again just to show you. And the reason I put the 3 first is because it seems when we give you the data, the big number is always the higher trial. And I always like putting the big number over the little number. Because if I put the big number over the little number, I'm going to get a number greater than 1. You know, 1.5 or 3 or 4, something like that. If I put the information in upside down, then I'm going to get a decimal number, and it makes it difficult to see the relationship. If you're dealing with whole numbers, the relationship becomes very easy. Okay, so I'm going to be doing x is equal to the log of rate 3 over rate 1 divided by the log of concentration of ClO2 3 over concentration of ClO2 1. Now I just transferred our general equation to this specific situation. Are we okay with this? I'm not dealing with 2's and 1's anymore. I'm dealing with trial 3 and trial 1. I'm just labeling it up. So let's put the numbers in. Log, and now I need you to help me with, what's R3? Yeah, go ahead, Ben. 10 to the negative 3, 2, and what is the R1? 1.3 times 10 to the negative 3, all right? And we will then keep on going, filling in our stuff. Log, what's concentration 3? 0.045, and what's concentration 1? 0.015. All right, and that's equal to x. Now, some of you might want to pound this through a calculator at first, but let's do the calculation first, and I really encourage you to do this. What is that first division? What's that number get me on the top? Anybody do that yet? $1.16. Yeah, what do you got? Yep, that's all I want. Just the number. 8.923. All right. So it's pretty close to 9, right? We'll write it in. 8.923. That's pretty good. And that has to do with the fact that we don't have another digit on the end. Did this have another digit on the end of it? No? All right, that's fine. What do we have for the other one? on the bottom. Sorry? 0.045 divided by 0.015. Yep. 3. We're going to be giving you nice numbers. If this was 9 and this was 3, then really what we're asking is, what exponent with the 3 is going to make it 9? That's really what's coming out of it. If we were to write this in that other equation before we wrote the log method, you would essentially have the rate 8.93 is equal to, and then the concentrations, 3 to the exponent x. All right? It's essentially what it's asking. Then when we do the log, we bring the x out front. What do we get there for x? Calculating it out. Yep. We get 2, right? Because 3 to exponent, yep, so we get 2. All right? So if that was 9, 3 squared, 9. It essentially means if I, double the if I triple the concentration, I'm getting 9 times the rate. It's a squared relationship. Okay? Now we do the exact same thing except for the other value. And I'm going to clear the screen one more time as well. Do we all have the values for that? All those numbers? So I'm going to clear this, clear ink. So for OH minus, what trials am I going to use again? Yep. 1 and 2? 1 and 2? So trials 1 and 2, usually I put 2 and 1, it doesn't matter. That means y, oops, that's a horrendous y, is equal to log, the rates go on the top, R2 over R1, log, and then the concentrations, OH minus 2, OH minus 1. Crash through gives you the exponent. And you could tell me all that stuff, but it would be much easier if you just told me what y was. We'll pause for calculation. Again, I like to have the bigger number on top and the bottom number, or the second number on the bottom, and the smaller number on the bottom. That gives you whole numbers. But be very careful. In a university situation, and actually, I wouldn't put it past our new textbook because I remember for some of those Hess's law problems, they put some doozies in there. You actually can have an exponent that is a decimal. You can have a 0.5. So when I say put the bigger one on the top, you can't trade them around. Whatever 2 is has to be on the top, and whatever 1 is has to be on the bottom. And if it's a decimal exponent, it'll actually have one that's smaller on the top, right, versus one that's bigger on the top. So you can't switch them to make it nice, like bigger on the top, smaller on the bottom. Whatever you pick as being the top, or R2 for this one, you must put the concentration that goes with that in 2. You can't be swapping them around, right? I wouldn't give you any decimal exponent, but like I said, the textbook during Hess's law problems, there was a couple of them that were pretty mean. Who knows? They might throw a curveball at you. So I tell you, I like to put the big number then the small number to get a whole number. But if it actually decreases the rate, it may end up with a small number over big number as the other expression. So the most important thing is keep your 2's with your 2's and your 1's with your 1's. All right? Once you pick it. What do we have for an exponent here? What do we got? Jess? 1? So it's not that it didn't do anything, but it doubled and doubled or something like that. Is that what it was? Excellent. So once you've got the 2 exponents, rate is equal to K concentration of ClO2 squared concentration of OH minus to the exponent 1, which doesn't need to be written, but we'll write it anyway. Now, I'm sure the final part to this little example was determine the K, right? Once you've determined the exponents, just pick whichever trial you'd like. I always just pick trial number 1. Substitute the data in for all the concentrations and the rate and solve for K. Doesn't matter which trial you pick. We're going to make all the numbers nice. In a real experiment, each trial would give it slightly different value for K, and if we did it right, we would straighten a curve and we'd get a slope to a line to solve the K, but you're just being introduced to it. We're just going to be solving it here. So again, rate divided by the concentration of ClO2 squared over the concentration of OH to the exponent 1 is going to be equal to K. And without me flipping back slides, I'm sure someone could tell me what that K is. And I don't know how many significant digits we working with here, 2 or 3? And again, like I said, K can have all kinds of different units. We're not going to worry about that in this course. Somebody have a K there? What do we got? 231.1. And how many significant digits are in the rest of our numbers? 2 is the lowest, so 231, so 230, right? And I guess best would be 2.3 times 10 to the 2, right, equals K. Ks can have all kinds of ranges of size. Fundamentally, the K really is what tells us how fast that reaction is going. If the reaction goes super quickly, then the K will be large. If the reaction is a really slow one, the K can be phenomenally small, right? So you really have no gauge on what the K is until you do the calculation. So that means we can actually write down the official rate law expression. Rate is equal to 2.3 times 10 to the 2 times the concentration of ClO2 squared times the concentration of OH minus to the exponent 1. So that's the rate law expression. I don't think it asks us to use this to calculate a rate. Did it ask us in this question? We could have an add-on part. Now calculate the rate. If the concentrations were, we give you 2 concentrations, you just put it in your rate law expression and you'd get a rate. All right? Okay? So that's how you do that. We're going to do one more just for practice. All right? Yeah, we are going to do one more for practice. And then I'm going to give you piles of more to do for practice. And the reason I'm showing you this one is that I also want to express to you, and you know what? Don't write down all this blah, 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 blah. Just write down the data. You know what to do with the data. Just put, like, determine the rate law. That's it. This data, if you recall, when I did Hess's law, I introduced you to that website that generates practice problems. You can also have it generate rate law problems. And this data is simply cut and pasted from that website. I just clicked supply me with a new problem, cut and pasted the data right into the PowerPoint. And again, the data is not complicated. Look at all these concentrations. They're fabulously perfect. Same with the rates. They're chosen to be mathematically perfect. This is the type of thing that you use to just practice. This reaction you can imagine as being as something as simple as A plus B plus C to get D and E. It really doesn't make any difference. But that general rate law is going to be K, A to the exponent X, B to the exponent Y, C to the exponent Z. And don't wait for me. I would start with something like this. 4A to the exponent X. Now you just got to pick some trials. What's got to be true now about B and C? Yep. They have to be constant. So I need to pick a trial where A is changing, two trials where A is changing and B and C are remaining constant. Did we track it? Right here in the middle, I think. 2 and 3, right? So then I would say trials 2 and 3. And once you get good at this, you should be able to plow through these pretty quickly. I don't even need to see the equation that says R2 over R, log of R2 over R1, blah, blah, blah. You can put it right in, as long as you put the rates at the top and the concentrations at the bottom. That's the main thing you can't screw up. So if I wanted to run this down here very, very efficiently, then I have to make sure I put my rate data on the top and my concentration data on the bottom. 2 and 3 rate data. I'm going to go 3 over 2 and look at what's happening to the rate. Already now we can already start to see something happening here, but we'll write it in anyway. Notice the rates are the same, so 6.4 times 10 to the minus 5 over 6.4 times 10 to the minus 5 and 0.050 0.150. Look at what happened when we changed the concept. Oh, I've got that upside down, don't I? Oh, look at, actually trial 3 is smaller, isn't it? Trial 3 is smaller. That's going to get me my decimal number. As long as I put them in together, it doesn't matter. As long as I put the 1 with the 1 and the 2 with the 2, it doesn't break it. It just means you got some decimal numbers in there. The log still works. It just means I'm going to have a fraction down here. But here, let's take a critical look. What happened to the rate when I changed the concentration? Stayed the same. What's the exponent when there's no effect on it? Yep, 0. So whether you plow through the calculation or whether you see that, I don't care. But as soon as you take the log of 1, what's the log of 1 equal to? Yep, 0. So that tells you it's 0th order. It turns out that A has no effect on the rate. And there's multiple ways you can see that. You can see that here. The rate doesn't change when I change this. That's no effect. That's a 0th order effect. Or if you plow on through with your calculations, you get 0. That's fabulous. Either way. For B, again, don't wait for me. No. Yeah. 2 and 4. Two and 4. I like to put the big rate on the top, and that's this guy, which means I'm going to have 4 over 2. But again, it doesn't matter as long as I keep them together. Big on the top, so that one on the top, that one on the bottom. Y is equal to log 1.3 times 10 to the minus 4 over 6.4 times 10 to the minus 5 log 0.50 over 0.25. Again, you can plow through it, but I think you're going to see double and double, right? 2 and 2, right? So if one doubles and the other one doubles, what's the exponent? Yep. Yeah, exponent 1. If one doubles and the other one doubles, that's an exponent 1. And you push that through your log-log calculation, and you should get a 1. Two and 3, 2 and 4, so I think the only possibility we got left is 1 and 4. 1 and 4. And 1 and 4. 2.6 to the minus 4 is bigger than 1.3 to the minus 4. So I'd likely put 1s at the top and 4s at the bottom, and then there that goes with it. 1 on the top and 0.5. Yeah, that's going to work. .6 times 10 to the minus 4. 1.3 times 10 to the minus 4. Notice the times 10 to the minus 4 really cancel out. Really, we've got 2.6 over 1.3. That's a doubling, right? We've doubled it. We've doubled the rate, and what did we do to the concentration? Log 1.0 over log 0.5, and it looks like we've doubled that as well. So again, keep that in mind. Even though we're not giving you mean numbers, the log-log method works, but if we double the rate when we double the concentration, what's the exponent? Even without putting it in the equation, what's it going to be? 1, right? So the log-log method is there. You know, if you're not good at seeing that relationship, it means you can mathematically just pound it through and get it. But keep an eye on it. We should have knowledge of that. Therefore, I can say then that the rate is equal to some constant k, and I really don't even need to put that a factor in there because it's equal to 1. All right, I'm going to write it in just because we did calculate it, but that whole thing is equal to 1. It's not even going to come into play when we figure out the k value. Times b to the exponent 1 times c to the exponent 1. All right, and I know I'm really squeezing this down into the bottom, but I might as well keep going. It's a mess anyway. Again, if I want to find k, I'm going to divide these things off under the r, but that a to the exponent 0, that thing is equal to 1. I don't need to keep it in there anymore. So really, to find the rate, to find the k, I'm going to take that rate number and I'm going to divide it, and that's horrendous. I don't even have it underneath the line. I'm going to divide it by the concentration of b to the exponent 1 and the concentration of c to the exponent 1. That's terrible, isn't it? That is absolutely terrible. But hey, if you guys can have a Monday morning, then I can too. Does somebody have a value for k? So I can squeeze it way underneath here. K is equal to, oh, look at there, not even equal to. Just pick the first row, stick the numbers in. Jess, what do you got? 5.2 times 10 to the negative 4? 5.2 times 10 to the negative 4. And realistically, I should rewrite that rate law expression with that number in it, but as you can see, I've squeezed every last bit of space out of that little slide there, so I'm not going to do that. You can rewrite it. And again, there could be an add-on question. What if the concentrations of A, B, and C were, what's the rate? Just put it into the equation. Okay? All right. All right. And that's that. Lots of homework problems. Again, the textbook came up with all kinds of problems. And when I, at the end of last year, got the new textbook and decided that, hey, the textbook's got lots of problems. It's got plenty of them. They don't need any other practice problems. I said, hey, you could find the extra worksheet online. And then I forgot I decided to do that, and I photocopied the extra worksheet. So here's the extra worksheet anyway. And as you guys know, practice makes perfect. Do what you feel you need to do in order to master this skill. And that's what we're essentially asking here. 4, 1, 2, 3, 4. There you go. Again, that's that same website that I introduced you when I showed you Hess's law. All kinds of just computer-generated practice problems. Again, you know, I've given you piles of stuff. I don't know if you need to go to that, but that's there, right? That's what that is.